we're all here then. So yeah, this is the speaking qualifier of Jaskaran. And so please take it away.
Awesome. Let's start again. Okay, well, good afternoon, everybody. Thank you for logging in to see my presentation. So today I'll be talking about my recent research on analysis of deadlocks in multi-robot systems. So just to give you a preview of what I mean by that, here's a short video demonstrating how these robots, while trying to navigate their goal positions, end up falling in this jam. So throughout this presentation, we'll try to deconstruct what's happening here and try to investigate the underlying physics that are at play and how we can resolve these jams by understanding the physics. Okay, so this is the outline of this presentation. I plan to revisit the slide every now and then just to remind ourselves where we are and keep track of where we are and make sure that everybody's on the same page. So let me walk you through what motivated this work. Multi-robot systems have been used for many tasks, such as search and rescue, exploration, and coverage. Now, generally, what happens is that the controllers that these robots are using for these tasks are a combination of a primary task-based control and a reactive collision avoidance mechanism. But this combination tends to be hand-engineered at some times, and because of that, it can prevent satisfaction of the original task due to conflicts. Robots may stop moving to maintain safety, and as a result, they can end up falling in deadlocks. And this observation has been noted in several of these works. In fact, many of these works are recent from the last 3 or 4 years. And so given this, we wanted to formally investigate why do deadlocks occur? What is the underlying mechanics behind the incidence of deadlocks? And how can we use this information to resolve deadlocks? So in this presentation, I will try to walk you through some of the answers to these questions that we found along the way. Okay, so let me summarize the main contributions of our work. Okay, so firstly, we provide a mechanism to analyze long-term behavior of reactive optimization-based controllers. In this presentation, we are primarily focusing on control barrier function-based quadratic programs, which are optimization-based controllers and have been very successful recently for synthesizing safe controls for UAVs and legged robots. But in addition to these systems, they've also been used for multi-robot systems, and that is primarily the focus of our presentation. So CBFQPs, that is short for control barrier function-based quadratic programs, are the underlying control synthesis module that the robots in our multi-robot system will be using. So we demonstrate that when these controllers are used for collision avoidance, in addition to goal stabilization in multi-robot systems, they can cause deadlocks. And particularly, we show that it is the symmetric initial and goal positions. So when there's geometric symmetry in the initial and goal positions of robots, that is a scenario that is particularly susceptible to deadlock. We're not saying that asymmetric situations do not result in deadlock. We're only saying that symmetric ones definitely do. We provide an algorithmic approach to analyze geometric characteristics of a system in deadlock. And we use tools from duality theory and KKT conditions to characterize some of the properties of geometric configurations in deadlock. And using these characteristics, we devise an algorithm to resolve deadlocks. All right. So let me go through some prior work and review some terminology from avoidance control and goal stabilization. And the aim here is just to make sure that all of us are on the same page. Since CBFQPs is a relatively recent subject, there's lots of jargon that is used here. And I just want to make sure that all of us throughout the presentation know what I'm referring to. So everything that I'm going to be presenting in this particular section is going to be on prior work. Okay, so let's see the setup. We have N robots in the plane. And just to make things simple, we're going to focus on just one ego robot, that is robot I, that is shown in blue color here. And our aim is to make sure that this robot reaches a destination position, that is P sub di, while avoiding collisions with every other robot that is shown in gray. Now, the same must hold true for every other robot in the system as well. So each other robot, let's say the gray robot, will have a goal of its own, and it must avoid collisions with every other robot in the system. So we assume that all these robots are velocity controlled, so they follow single integrator dynamics, which is given by P dot equals to UI. And as far as this dynamical system is concerned, this is the best that we can ask for. And the reason for that is because it's linear, it's controllable, it is a single integrator, sorry, it's first order, and it's decoupled. You can control X and Y independently. So this is as best as it gets. And as it turns out, this is a good model for kinematic robots operating in lab environments, perhaps not maybe on the road, but definitely in the lab environments, this is a good model. So in addition to this model, we assume that we have a prescribed reference control, which is U cap, which is simply a proportional controller given by negative Kp, P minus PD. And if you know anything about linear systems theory, this control in conjunction with this dynamical model guarantees exponential stabilization of the robot to its goal. So if you use this control here, it's guaranteed as long as Kp is positive, that the robot will stabilize to the goal position. And the catch, however, is that this control does not ensure collision-free motions between pairs of robots. So how do we pose that requirement? Well, we say that the distance between the robots be at least d sub s, where d sub s is a desired safety margin. And this has to hold true for every pair of robots. And this is a very nominal request to ask for. And to pose that request, we are posing this safety index that is pairwise. We call it h sub ij. And we say that robots I and j are collision-free if and only if h sub ij is non-negative. Now, h sub ij is known as a control barrier function, or a CBF. All right, so what have we seen here? As I said earlier, for I and j to be collision-free, we need h sub ij to be non-negative. Now, obviously, if it is non-negative at the current time instant, we also want to make sure that the control that we synthesize on the robots makes sure that the h sub ij remains non-negative at the next time instant as well. And the way that has been done in prior work is by enforcing this derivative requirement on h sub ij. So if by ensuring that h dot sub ij is greater than negative gamma times h sub ij, we have guarantees on the fact that h sub ij will remain non-negative at the next time instant. Now, this inequality, or a differential inequality, can be converted to constraints on the controls of robots I and j. So if the controls of robots I and j, this is the constraint on the control of robot I, and this is the constraint on the control of robot j. If the controls of robot I and j satisfy these constraints, then this condition will be guaranteed, and in turn, it will ensure that h sub ij remains non-negative. So these constraints are half space constraints. So the admissible space of feasible controls that satisfies these constraints is convex. So what have we seen so far? I said that we have a reference control for reaching a goal that was U cap, which is a proportional controller. So by itself, it guarantees stabilization of the robot at the goal. And just now we saw some constraints to ensure safety. So we have two things here. How do we mediate between them? The way to do that is to pose a quadratic program or an optimization problem that minimizes the deviation from the reference control U cap subject to the safety constraint. So any control that is minimally far away from U cap such that it satisfies the safety constraints will ensure that the motions of the robots are mutually collision-free, in addition to trying to maximize the deviation of the robot from the path that delivers the robot to the goal. So just remember here that U cap is the reference control that delivers the robot to its goal. It gets overridden by UI star, which is what the robots will end up following. AIJ is a vector that connects the robot I to robot J. I'll have more illustrations in the next slide, but I just want to tell you AIJ is something that shows up in the constraints. And BIJ is the excess distance that is left relative to the safety margin between robots I and J. Okay, so does this approach work in simulations? So let me show you an example demonstrating that yes, it does. So here we have 4 robots. And what I want to do is I want a robot of color X to go to a destination position of color X. So the robot of pink color should go here, robot of color cyan should go here, the one in red should go here, and the one in blue should go here. So if I play this video, you can see that all the robots are able to safely navigate around one another and reach their home positions safely. So let me show you another example. In this video, the initial positions of the robots are the same as the ones in this video. The only difference is that the goal positions of the red and cyan robot are different. So for the red robot, the goal was here. For the red robot, the goal is here. For the cyan robot, the goal was here. Whereas in this video, for the cyan robot, the goal is here. So if I run the same strategy, this one from prior work on these robots, the algorithm fails to deliver the robots to their goals. So I just want to be clear here that this result does not say that the algorithm failed to work. We have no reason whatsoever to mathematically criticize the correctness of this algorithm because the algorithm only promised that safety will be guaranteed. And rightfully so, it did deliver on those promises. The only thing that it didn't guarantee was that the robots will not stabilize to their goal positions, just because that was expressed as a cost function in this optimization, not as a constraint. So because of that, this result is mathematically correct. Now, it's another story that this result is not to our liking because the robot stalled before reaching their goals. And this is precisely what deadlock is about. And so this is the kind of phenomenon that we're trying to diagnose and analyze in this talk. Okay, so does this work in practice? Yes, deadlock does occur in practice as well. So I'm going to show you an experiment that we did in the lab. We have 3 robots here, and we want, this is robot 2. We want this robot 2 to go to goal position 2, robot 1 to go to goal position 1, and robot 3 to go to goal position 3. I purposefully added enough symmetry in the system such that deadlock will occur. And if I play this video, you'll notice that while these robots are trying to shoot for the antipodal positions, they end up falling in deadlock. So now I'm going to add a manual perturbation to and intervene so that I can remove that symmetry. And once that perturbation is strong enough, these robots, without colliding with one another, are able to go to their goal positions. Now, naturally, it's not possible that this intervention be there every time. I'm not going to be there to perturb these robots. So why did this occur in the first place itself? Now, before answering that question, let me define the underlying problem here, which is that of deadlock mathematically, just so that we're all on the same page on what it means for robots to be in deadlock in more formal terms. Okay, so we say that a robot I is in deadlock if the optimal control UI star is 0, but the nominal control UI cap is not 0. So the prescribed reference control UI cap is non-zero only when the robot is not at its goal. So in a way, this definition is saying that the advisory wants the robot to keep moving, but the actual control that ends up getting implemented on the robot is advising the robots to stop. So UI star equals to 0 means that the QP, which is the optimization problem, is outputting 0, so that the robot should stop moving. But UI cap not equals to 0 wants the robot to continue moving. But the QP says no. So there is a conflict between the advisory and the actual control that ends up getting implemented on the robot. Why does this conflict occur? To answer that question, I'm going to look at the closed loop dynamics of the robot before deadlock occurs. Obviously, naturally, we can't look at the dynamics after deadlock occurs because the damage is already done. We need to see what happens before deadlock. So our contributions of my work begin from the next slide. So we're going to analyze what's happening in the closed loop dynamics before the incidence of this event. Well, as I said, we need to look at the closed loop dynamics of the system. But to do the closed loop analysis, I need an analytical expression of the control as a function of the states. But on the top, you see the optimization problem that each robot is solving to synthesize the safe controllers that ensure maximal movement towards the goal. Given the fact that you have an optimization problem in the loop, you don't get an expression of the control UI star as a function of the states. We cannot use our favorite Lyapunov-like tools from systems theory because UI star depends in an implicit indirect way on the variables P and the positions of other robots. So what I'm going to do now is I'm going to fix that and derive an expression intuitively. So let's look at the geometry of the system. We have several robots here. I told you that U cap is a reference control that causes attraction of the robot to the goal, which is UI cap here. Because this is the primary task, we need to make sure that the optimal control has some component of the task-based control, which is UI cap. In addition, I also said that Aij is a vector that connects the robot from robot I to robot J. Naturally, we don't want the robot I to go along Aij because that would result in collision with the obstacle. We want the robot to go opposite to Aij, so along negative Aij. But we do want the robot to go along UI cap because that is what will ensure movement towards the destination. So in addition to this, I'm going to add a component that is negative mu ij times aij, which ensures movement opposite to this vector. And mu ij is just some weight, which is non-negative. It has to be non-negative just to make sure that I does not get up and end up getting attracted to j. That would be antithetical to the collision avoidance requirement. The other purpose that mu serves is that it makes the units consistent. Like this is the unit of velocity and this is the units of position. So mu has units of 1/2. Another purpose that mu ij serves, it ranks the relative risk associated with several obstacles. So if there's an obstacle that is several miles away, maybe I don't need to worry about collisions with that obstacle. So mu ij would be 0 for that one. And if there's an obstacle that's very close to me, I'll set mu ij to a very large and positive number just so that I duly account for collisions with that obstacle. So it has to be non-negative. And now there's several robots in the system, so I have to sum these repulsive forces from every other robot in the system. Is there anything else that we know about the control? Well, what we also know is that the fact that this control is coming from this optimization problem means that it must satisfy these safety constraints. This expression was derived in an ad hoc way, using some intuitive arguments. But we definitely know that if this is the expression, then it has to satisfy these constraints. So just to summarize, there are 3 things we saw here. I said that the optimal control is sum of 2 components. One is attraction to the goal, and one is repulsion from every other robot in the system. From the perspective of the ego robot, I can just call them obstacles. Mu ij, the weights have to be non-negative for valid repulsion. If they are negative, then you'll get attracted to the obstacle. That's not good. And the third is that the control must satisfy safety constraints as well. There's 3 things here. Now, the claim is that this expression that I just derived in an ad hoc intuitive way is actually the solution to the optimization problem that we just saw. Now, why is that the case? Well, in optimization theory, there's something known as KKT conditions, which are necessary and sufficient conditions of optimality. So I say that UI star is a solution to this optimization problem, if and only if UI star satisfies some constraints or equations. And those equations are basically the KKT conditions of this optimization problem. And just to make sure this optimization problem is convex, that is why if and only if can be said. Otherwise, they're just necessary. So the first condition, that stationarity, is precisely saying that the optimal control is the sum of attractive and repulsive forces. UI cap is the one that's characterizing attraction to the goal, and this is repulsion from obstacles. Second condition, this primal feasibility, is saying that UI cap satisfies safety constraints. So UI star satisfies safety constraints. Dual feasibility saying that the weights have to be non-negative, which we motivated by saying that the repulsions have to be valid. And in KKT conditions' language, mu I star is known as the Lagrange multiplier of this optimization problem. And the fourth condition is complementary slackness, which I haven't motivated just yet. It's very straightforward. What it says is the following. So remember that we said that the optimal control has repulsive components from all robots in the system, in addition to the attraction to the goal. What complementary slackness is saying is that you only need repulsive forces from just some obstacles that are called active, and the rest of the obstacles can be ignored, can be neglected. So in this slide, the red ones are the active obstacles that are actually accounted for while calculating the optimal control of the ego robot, and the gray ones can be neglected. And from my empirical simulations, I've seen that the active ones are the robots that sort of fall in the way of the ego robot trying to go to the goal. And that's because these robots, which are already behind me, are not going to pose such a threat, imminent threat of collision, as those robots that are falling in my way of going to the goal. So I need to duly account for repulsions from the ones that are going to end up, or potentially going to end up falling in my way. So what have we seen so far? I said that all the robots from the perspective of the ego robot can be partitioned into two sets. There's one set that's active, which is the set that I worry about for collisions, and I account for repulsive forces from that set while calculating my optimal control. I said that the optimal control has two components. One is attraction to the goal, and the other is repulsion from the active obstacles. And as far as whether the strategy works or not, I showed you a simulation in which it does work, so it delivers the robots safely to their goals. But then there's some situations in which it does not work, where depending on the initial positions or goal locations, robots can end up falling in a deadlock. So using this control, that is go to goal and repel from active obstacles, can result in deadlocks as well. And now all the analysis that we've seen is enough machinery for us to start to figure out why this is happening. So the question that I'm going to answer is that given this control, can you tell me when will deadlock occur? Instead of answering when it will occur, let me first answer the question, when does it necessarily occur? Now, this second question is much easier to answer than the first question. I'm not going to characterize every situation in the world where deadlock occurs. I'm only going to characterize a handful of situations where I can guarantee that it will occur. So I'll try to convince you with a small example that whenever there is symmetry in the initial conditions and goals, deadlock definitely occurs. And I'm saying small example because I will consider only two robots. That's because if there's so many robots in the system, the analysis becomes very amorphous because there are multiple moving parts here. And I've done this for 2 robots. I've also done this for 3 robots, but I want to convey the idea here. So we'll show you the analysis for 2. And technically 2 is still multi, even though it's the least you need to call it multi. All right, so when does a 2 robot system necessarily fall in deadlock? The main result is that if the 2 robots and their goal positions are shown as in this picture here, then deadlock will definitely occur. So we have robot 1, which is in red color. It's trying to go to its goal location, that's PD1, also in red color. We have robot 2 that is shown in blue color, and it's trying to go to its goal location, that's PD2, that is also in blue color. These robots are headed towards each other. And I'm saying that this is an example of a situation where deadlock will definitely occur. So let me play this video. So given the initial positions and goals, CBFQP results in deadlock. So what is going on here? Well, let's see that in more, let's examine that in more detail. So the analysis of the motion of these 2 robots can be broken down into several sequential phases, which depend on whether I, as the ego robot, perceive the other robot as active or not. And so in the following discussion, when I say that I, as the ego robot, am worried about collisions with the other robot, that means that I do perceive the other robot as active. And if I'm not worried, that robot can be ignored for calculating my optimal control. Okay, so the analysis begins as follows. We say that there's phase 0 first, which starts at t equals to 0. So it's just an instantaneous phase. It just lasts for 1 instant. And at t equals to 0, I say that the robots are not worried about collisions with each other. Then, obviously, this phase is not going to end right away. This pattern is going to continue for some time. And phase 1 starts when both robots continue to be not worried about collisions with each other. Can everybody mute themselves, please? Okay. And then phase 2 starts, where one robot begins to worry about collision with the other, whereas the other robot is still not worried about collision with the first robot. And then you have phase 3, where both robots end up worrying about collisions with the other. And it is in this phase that both these robots end up falling in deadlock. All right. So I was saying that there's this notion of a robot being active with respect to me. There's this notion of a robot, of me worrying about collisions with the other robot. What does it mathematically mean? What does it geometrically mean? So just to recall, I said that the control input is always the result of this optimization problem that all these robots are solving. For the two robot case, there's just going to be one constraint per robot, right? Because I'm only going to think about collisions with the other robots. There's just like one constraint. Okay, let me see if I can mute everybody. Okay, well, thank you. So yeah, so for the two robot case, there's just going to be one constraint per ego robot. If it so happens that the prescribed nominal control satisfies this constraint itself, then the optimization problem will just return u cap itself, simply because if I'm saying that there is a reference with respect to which I want to be minimally far, I'm also saying that the reference itself is satisfying the constraint, then the optimal will be attained at the reference itself at zero cost. It doesn't get any lower than that. So the answer to this optimization problem will be the reference control u cap itself if the reference control satisfies the constraint. Now, what is more interesting is that the reference control u cap satisfies this constraint if and only if the distance between the robots is more than a certain critical distance, that is beta I. So what I'm saying here is that the robot, let's say this red robot here, can use its reference control, pretending as though there isn't any other robot in the system. But it can only do that if and only if the distance between these two robots is more than the critical distance that robot one considers as a threshold. So each robot will have its own critical distance because that depends on the parameters of the control of each robot, the proportional gain or the initial distance to the goal. But this critical distance is going to be unique to each individual robot. And that is using this criteria, a robot criterion, the robot will be able to evaluate whether another robot is a source of worry for me or not. So now that we know what it means geometrically to worry, let's start with phase 0 in more detail. So at t equals to 0, I'm saying that if the distance between the robots is greater than the critical distance of robot 1, meaning that the reference control of robot 1 is satisfying the collision avoidance constraint directly, then robot 1 can use the reference control. So here, this green dot is the inter-robot distance, which is shown here. Blue dot is the critical distance of robot 1, and you can see the green is higher than blue, so the inter-robot distance is more than the critical distance. So we are allowed to use the reference control for robot 1. The same also holds true for robot 2. The inter-robot distance is greater than the critical distance of robot 2, which is shown in mustard here. So robot 2 can also use its reference control. Now, obviously, this pattern is going to continue for some time. It's not going to be that at one instant I'm not worried and right at the next instant I suddenly start thinking about collisions. So I'm saying that until time t equals to t1, the inter-robot distance remains greater than the critical distance of robot 1. So robot 1 can use its reference control. That holds true for robot 2 as well. The inter-robot distance remains greater than the critical distance of robot 2. So robot 2 can also use its reference control. But eventually, there does come a time, t1, which is shown here, where the inter-robot distance becomes equal to the critical distance of robot 1. And why it became equal to the critical distance of robot 1 is because robot 1 was vigorous to begin with. It had a higher proportional gain. So naturally, if it was vigorous, its critical distance is going to be higher because the inter-robot distance is going to fall quickly compared to how the critical distance changes with time. So because of this, robot 1 now starts to worry about collisions with robot 2 because the critical distance has been reached. As far as robot 2 is concerned, the inter-robot distance is still greater than what robot 2 perceives to be a threshold that is too close for comfort. So robot 2 is comfortable in using its reference control. So I said that robot 1 has started to worry the optimal control is not going to be equal to the reference control of robot 1. But robot 2 is still not bothered about 1 because the inter-robot distance is greater than what robot 2 perceives as is too close for comfort. So this is phase 2. But obviously, eventually there does come a time when the inter-robot distance becomes equal to the critical distance of robot 2, that is time t2 here. And that's when robot 2 begins to worry about 1. So 1 was already worried about 2, 2 has begun to worry about 1. That's when phase 3 starts, where both robots perceive the other robot as active. And we show in the paper that it is in this phase that the distance between the robots exponentially converges to the safety margin that is d sub s. And because it converges to the safety margin, both robots, they end up falling in deadlock. So the controls will converge to 0. And because of that, they fall in deadlock. So what have we seen so far? I said that at any time during the motion of the robots, whether I as an ego robot perceive the other robot as active or not, meaning whether I worry about collisions with the other robot or not, depends on how far that robot is from me. And I will have a critical distance against which I can do this comparison to figure out whether the other robot is a source of worry or not. In deadlock, however, when both robots have fallen in deadlock, both robots are worried about collisions with every other robot. And they're perceiving the other robot as active. And the robots are grazing each other. They're exactly separated by the safety margin. And the third thing, which is, I'm just stating that, is that deadlock occurs to prevent collisions. Because if the robots were to move, two things could occur. Either collisions would happen, which is what we don't want, or the robot's motion will incur more cost. So it's not that economic with respect to the cost function that we had in the optimization problem. All right, so now that we have fallen in deadlock, let me investigate some geometric properties of the robots once they are already in deadlock. So this analysis that I'm going to describe next is independent of the initial conditions. It's independent of the destination positions of the robot. It's just starting with a necessary condition saying that assume robots are in deadlock. What can you tell me about their positions? Okay, so given that a team of n robots is in system deadlock, meaning that everybody is in deadlock, first question I'm asking is that what is the number of geometric configurations that are admissible? The reason we care about this question is because if this number is small, let's say that there are two robots, they're in deadlock, what is the number of configurations possible? The answer to that question is 1. Good. If the answer to this question stays small for, let's say, 5 robots and 15 robots, then I can think about enumerating all those configurations one by one and figure out or devise a strategy for resolving deadlocks for each of those configurations. But the catch is that unfortunately that number is not small. So use some ideas from geometric graph theory and combinatorics to find that there's a very large lower bound. For n robots, this lower bound is n plus 1 times n minus 1 factorial. And we know that factorial overtakes exponential, so it's worse than exponential. And this combinatorial complexity is going to create problems in resolving deadlock, simply because for 4 robots itself, the answer to this question is like 40. For 5 robots, it's something like 150. So because of the explosion in the number of possible positions that the robots can be in that all sort of satisfy the criteria of being in deadlock, it's hard to devise a resolution strategy for each and every one of these configurations. And so that is why in this work, we don't have a universal n robot resolution mechanism, but is it a question? Okay, but that's okay because at least we know what the underlying bottleneck is. So with that in mind, let's consider a small number of robots. We'll start with 2. And for 2 robots, one of the things that we can say is that the system deadlock set is non-empty, meaning that there always will exist some states that will all satisfy the criteria of these 2 robots being in deadlock. I can give you a family of states that will all definitely be in deadlock. Now, whether these states are reachable or not is a different question, but these states will satisfy the criteria of being in deadlock. And one of the properties of these states is that the robots will be separated by the distance ds. So P1, and the other property is that these states will always lie on the line segment connecting the goal positions, as you see here. So you have the goal 2 here, goal 1 here, and the robots will always be collinear with the goal positions. The second property for two robots is that the robots are at the verge of colliding with one another, so they're grazing each other. And this makes intuitive sense, because if these robots had wiggle room between them, suppose they were not, suppose they were in deadlock, but they had wiggle room between them, then they would still slowly be able to move towards one another. And the fact that they could move would contradict the definition of deadlock. So that is why it stands to reason that once they are in deadlock, they've exhausted all the wiggle room, and that's when they're grazing each other. And because of the fact that they're grazing each other and just at the brink of violating safety, the state of the system is on the boundary of the safety set, which is shown here. So red is the unsafe region and green is the safe region. We can also say these properties about three robots. System deadlock set is non-empty. I can propose a set of candidate states that will satisfy the criteria of three robots being in deadlock. And the robots are going to be safety margin apart. For three robots, there are two qualitative categories of configurations possible. In the first category, all robots are grazing each other, so that's why they form an equilateral triangle. In the second category, it's exactly two pairs that are grazing each other. So J and K are not perceiving each other as active, but J and I are, and I and K are. So now that we've seen some of the properties of 2 and 3 robot deadlock, the question is, what can we do with these properties to resolve deadlock? So now I'm going to look at this after deadlock phase, which, given these properties, exists, because the fact that I'm going to talk about after deadlock means that we are looking at some strategies to resolve deadlock. Okay, so as I said, given all these properties, how can we leverage them to resolve deadlock? For the two robot deadlock, I told you two things. The first one was that once the robots are in deadlock, the robots would be grazing each other. They're exactly separated by the safety margin. And that the robots and their goal positions are collinear. These two observations can be summarized into one, saying that the vector that is connecting the robots, so one that's connecting P1 to P2, is anti-parallel to the vector connecting their respective goals. So PD1 to PD2 is a vector that's shown in red here. This P1 to P2 is the vector that's shown in black here. So the one in red is anti-parallel to the one in black. And what I want to do to resolve deadlock is to make sure that these two vectors are parallel to each other. And the way to do that is to rotate this one such that it aligns with the red one. So I'll explain why I'm doing that, but just for now, I'm telling you that this is what I'm going to do. And this will make sense when I tell you the full strategy to resolve deadlock. Okay. So I'm proposing a three-phase strategy to resolve deadlock. The first phase is using the original CBF QP-based controllers. If these controllers don't result in robots falling in deadlock well enough, we don't have to worry about deadlock in the first place. So let's just use these controllers as you normally would, because they come with good properties. So why not use them? But if it so happens that they do end up resulting in deadlock, what I'm going to do is I have some way to check whether this has occurred. And I'll switch to phase 2, in which I'll use feedback linearization. It's a technique from nonlinear systems theory to make sure that those vectors align with one another. So there was one vector connecting the goal of 1 to 2, and the other vector that's connecting the robot 1 to 2, and these vectors are anti-parallel. I want to make sure that both these vectors are parallel. So I'll use feedback linearization to sort of interpret the assembly of two robots as a rod, and I'll generate equal moments, equal torques on both sides to make sure that this assembly rotates as if it was a rigid rod. And once this rotation is complete, which is guaranteed by the way feedback linearization works, I'll just use a prescribed, the reference PD proportional controller to deliver the robots to the goals. Throughout the entirety of the execution of this three-phase strategy, safety will always be guaranteed. The way we are constructing controllers in phase 2 and phase 3 are such that safety has to be guaranteed. So let's see this working in practice. We have two robots here. One is trying to go to this position, two is trying to go to this position. So I'm asking them to swap positions with one another. Obviously, the positions, initial positions and destinations are cherry picked so that deadlock occurs. It does. Then we switch to phase 2 when robots rotate around one another. And then they end up using phase 3, where they'll use their prescribed nominal controls to go to their goal positions. This also works in 3 robots. So I have robot 1 here that's trying to go to antipodal position, robot 2 here that's trying to go to its antipodal position, and robot 3 that's trying to go here. So it takes some time to check whether the rotation is complete, because I'll have some thresholds in my code to do that. So that was phase 3. Okay, so with that, I'd like to summarize everything that I've presented today. We analyzed long-term behavior of reactive optimization-based controllers using duality theory. We demonstrated that whenever there's geometric symmetry in the initial positions and goal locations of the robots, that constrains CBF QPs to generate velocities that inevitably cause deadlock. And then we used duality theory again to analyze configurations, possible configurations of robots when deadlock occurs. In future, we plan to extend this analysis to other reactive control synthesis methods, such as velocity obstacles. And in addition to that, we also plan to extend this analysis to end robot systems, but with arbitrary initial conditions, or relax some of the assumptions that we made before to prove the results. And with that, I'd like to thank you for listening to my presentation, and I would like to take questions now.
Cool. Thank you, Jaskaran.
Cool.
Katya, I think you're muted. Hello?
Yes, I was muted. Okay, so are there any questions? So first of all, we are going to take questions from the committee, and the kind of further away person in the committee, since Changyu and I are co-advisors. So Howie, you get to go first.
You know, it's funny. I always thought I was closer than the two of you in this relationship to Karen, but I guess publicly I have to find out that's not true. Okay, so yes, Karen, this was a great talk. And if you saw me typing during your talk, I was taking notes, which I'll share with Changlu and Katya afterwards. Okay. You did a wonderful job expressing an idea with rigor and putting forth a result. So I have a question. I have a bunch of questions for you, which you can offline, but let me ask one big question here. So while I was watching your talk, I was thinking about, what if we had some just giant centralized Uber planner, planning for everything, and we just optimize from there. To get your optimal controllers from all your robots that go from start to goal. And then the obvious answer as to why you don't do that is because the computational complexity would be horrific. So that's why you do something in a decentralized way, and then you deal with the deadlock as it comes. Right. So I'm wondering, is there a middle ground? Is there something where maybe you can only consider robots that come into close proximity of each other and plan in that joint space only for those limits? I'm recycling Glenn Wagner's idea of subdimensional expansion, but applying it to your problem. Could that be another means by which we can avoid deadlock, or even use that to characterize deadlock?
Right. So interesting that you brought subdimensional expansion because I was just reading about this morning. I was guessing, oh, I should know subdimensional expansion, but it wasn't enough time to read to understand that. So this is like just this morning, I was reading the abstract of Glenn's paper. Um, but uh, so I want to tell you one thing. So I've noticed from my simulations that when everything is centralized, then deadlock doesn't occur. So if all these robots, there was like a central oracle that was doing the calculation, then I didn't notice incidents of deadlock. I don't know why mathematically that is the case, but that's an observation which speaks to uh, which is an argument in favor of using some extent of centralization. Um, I think that the middle ground would be to have some robots in charge of some centralization in the team itself. So I, as one robot in the team, should be responsible for 4 robots around me to calculate their controls, and I tell them what they should be doing. And I will have another robot in the system which will be doing the same thing and calculating controls for other robots that are around that robot. And so I'm thinking that these 2 robots that are the leaders in the team can be sort of centralized, but amongst themselves, they will be decentralized. This is a strategy that comes to my mind right now.
Okay, and I wasn't trying to put you on the spot. So let me ask you one last question. It's an easy question, and I'll pass the baton. So in the geometry world, symmetry is kind of brittle. In other words, it's easy to break symmetry. And I was just curious here, and I realize you perturb your environments, your examples to break symmetry, and you use the words, if you perturb them enough. I was just wondering, in the examples where deadlock occur, can you give me an intuition as to how much you have to perturb things to avoid the deadlock in the first place? Or we always have examples where deadlock is inevitable anyway?
Right. So that's slightly difficult to answer because I noticed that in experiments with 2 robots, when I wanted these robots to go head on for each other, deadlock was not occurring at all in experiments. And I think that there was enough noise through Vicon or through something else that took care of swiveling these robots around. So that the deadlock set was quite unstable such that it could be exit quite quickly. With 3 robots, the perturbation had to be really strong, like small perturbations. That video, I just perturbed it twice, but I have videos in which I had to perturb it several times to get them out of deadlock. And the direction of perturbation also matters. I cannot have robots stretched out and then get attracted. It's like a springy system. You can interpret that. It has to be swiveled around. So it has to be normal to the nominal direction that the robots will be going.
Okay. Well, thank you. Thank you for this great talk.
Cool. Thank you.
Okay. So Wenhao?
Yeah, Jackie, thank you for the talk. It's great.
Awesome. Thank you.
I do have like 3 quick questions, and some may overlap with Howie's. Yeah, so my first question is regarding the before deadlock phase. Like you talk about different phase, and I was wondering just, do you have any explicit conditions on characterizing like if it is currently before deadlock and how we actually know the actual distance to determine whether the collision avoidance is active or not? So I'm just curious, like, do you have any like formalization on that?
To answer the first question about whether robots are in deadlock or not, what we do is we compare. Okay, let me take you to the definition of deadlock here. What we do is we compare UI star with some threshold delta. If it is smaller than delta, and if U cap is larger than delta, then yes, you are in deadlock. So these are hand engineered thresholds. That's what we do to compare whether to conclude whether the system is in deadlock or not. To answer the second question about when a robot perceives the other robot as active, yes, so the critical distances that I was talking about, they only depend on the proportional gain of the ego robot and the ego robot's initial distance to the goal. So these are pre-computable constant numbers that, they do change with time, but their behavior doesn't change with the motion of the robot as it is moving in the world. So they are pre-computable. And so, yes, it is possible to know whether I am currently perceiving another robot as an obstacle or not by calculating those critical distances ahead of time.
I see. Cool, thanks. Yeah, I was asking because like similar to the second question about the related work. So I don't know if you have seen like Magnus have another paper characterizing this deadlock, and they're
Right.
able to kind of like provide the random perturbation when there's a deadlock situation, or even like predict when the robot is about to enter the deadlock by looking at the geometry in the control space. So I just was
Right.
wondering like, can you comment on like what's the comparison over those kind of methods? Like, what is the advantages of yours?
Right. So, so the perturbation was not random. Actually, what they were doing was you were right in identifying that they figured out where in the control space the current optimal control is, and they they said that the optimum either occurs on the edge of the safety of the feasible controls or on the vertex of it, and um, the the difference is that we have guarantees that robots will stabilize to their goals and safety will be ensured during our resolution mechanism. But I'm not sure if those guarantees were provided in the paper. Maybe they hold, but the journal paper that I read, I don't remember. I don't think that they mentioned anything about guarantees during the resolution phase. And also, they didn't exploit these geometric properties that we derive from KKT analysis about things that hold in deadlock. So we are like explicitly exploiting those properties.
Right. Cool. Thanks. Yeah, I think that's actually partially answer my final questions. Like, so for now, you just discuss everything in the context of the CBF QP.
Right.
So, what's your thoughts over applying this method to like other collision avoidance method? Like for now, your KKT condition is developed by those constraints from the control parameter function. But if like people just doing like some general collision avoidance algorithm, like is there a way for you to come up with a general characterization of this deadlock situation? And yeah, can you comment on that?
Right. Yes. Let me. So I'll use this slide as an example to illustrate that. So this paper by Stepanovic et al. From UIUC, the control that this paper is using surprisingly looks similar to the control that we have. It has attractive components, it has repulsive components. So I do think that that same analysis can be applied to the work that they have done. And and their safe control synthesis is done using value functions and adding manually engineering attractive and repulsions, like not through an optimization, but hand engineering them. And they have proofs that this strategy will work. But they also talk about deadlocks in their context. And now, if we talk about velocity obstacles, I think that because velocity obstacles also admit a convex optimization form when computing the safe controls for every robot, I do think that the same analysis can be extended to velocity obstacles as well. I've tried to play around with that. It's slightly complicated, but I think if I were to work like super hard on velocity obstacles, then the same conclusions can be said about those things as well. And then there are other safe set methods like Changli's work, which can also be fit into the same format, and therefore this analysis can be applied to those safe set algorithms as well.
Yeah, yeah. I was asking because I'm just like thinking if it's possible to like develop some general, for example, energy function, or that can be represented by either control parameter function or velocity obstacles when you do the action analysis. But actually, they may correspond to some more general ideas of this kind of energy function or the local minima of this optimization type of solution.
Well, the thing is that we can't say anything. We can't say that deadlock is a local minimum because it's a convex optimization problem. So it has to be a global minimum of that. But there are some papers that call it a local minimum, and I take issue with that terminology because I'm not sure what is the function whose local minimum we ended up converging to when deadlock occurred, even though it has all the empirical properties that we share with what local minima are. Because we perturbed it slightly and it got resolved. That's how you resolve local minima as well. But I'm not quite sure about what is that mathematical function whose local minima we ended up converging to.
Mm-hmm. Okay, yeah, that makes sense. Thank you. I'll stop
Cool.
here.
Yeah, so Changyu, do you have any questions?
Yes, great talk. I just have one question which occurred to me. Maybe you have already tested before, but can you comment on what will happen if you change the objective function u minus ur reference square norm to
Right.
a quadratic form where the weight matrix is not identity?
It's a good point. Let's see. So all this analysis would stay the same because that would amount to rescaling the proportional gain of the reference controller. Because I can change coordinates, right? So you'll have u transpose q u, let's say, and then I can just do the Cholesky or whatever decomposition of q. And so then I can just define a new controller because that matrix has a positive definite, right? So what I'm saying is that I don't think that will not have deadlock because we introduced a positive definite weighting matrix. I'm saying that that will just amount um, to rescaling the proportional gain. It will be equivalent to that. That's that's what I can think right now.
Yeah, I agree that there will not, that the deadlock will not disappear, but maybe the characters may change, and it may be a nice future work.
Right, right. Yeah, that is true. I think characteristics will depend on that Q, but yeah, the critical distances, for example, would end up getting changing. Would end up getting changed.
Right. Cool. Great. That's my question.
Cool. Thank you.
Yeah, and I have a couple of comments, maybe more for future. So the one is I noticed that this work and also, you know, at the Robotarium and the ones that you showed are in 2D, right?
Right.
Now, does it make any sense to worry about 3D kinds of deadlocks? Or we can say, well, you know, they may not, I mean, not even study the phenomenon because we just have so much, you know, space there that these things may not occur. So that is one.
Right. Right. I think that yes, there is more room for robots to evade deadlock when you have more dimensions to work in. We did an experiment with Basti's group where we had a quadrotor, and it was I think it was the DJI drone that was headed. We use CBFs, and it was headed for a certain obstacle. So deadlock can occur with static obstacles as well. It can happen with one robot as well. So one robot and one obstacle is also a situation where it occurs. And yes, like so to be fair, like what we were doing was we were just making the quadrotor move in a plane. So it was still, even though it's a robot that's capable of moving in 3D, in that experiment it was only moving in a plane. So it's not answering your question.
Yeah, because I mean, I remember, and maybe I'm just totally hallucinating, but I thought there was collision, a rare event of two planes. I mean, in actuality, I think it was some years ago, and it was just like a total, you know, a total amazing rare event. I mean, you know, there are systems, of course, there are sensor or whatever whatever systems had gone, you know, and they were so quickly that the pilots could not. And there was, I think, if I recall correctly, maybe I'm wrong, but I have this vague impression that there was one collision like that. I mean, this is like this rarest of events, but and also, of course, if you have situations where you may have a cluttered situation, where, I mean, in civil aviation, obviously what you are going to have, you know, you have obviously these spaces that the controller obviously direct the airplanes, which spaces there are, obviously for this reason to avoid collisions. But if we look at future trends in this control, you know, air traffic control situation, as there have been various visionary kind of proposals for having not these very constrained things where you just the air traffic controllers kind of calculate the corridors and so on, you know, that people go the polygons, basically the 3D, you know, that direct the airplanes, but a more free kind of situation where now you don't have this. And there could be possibly, especially in cluttered airspace, you may have this as a real problem. That's why I'm bringing it up. It's a future kind of thing, but I think it may be interesting as a future kind of research problem to look at what may happen there in 3D in a cluttered space where you don't have much, place to go.
Right. But I mean, I find that interesting. I would tend to think that airplanes should just fly at different altitudes to.
Yeah, and that's what the air traffic controllers do, right? And that's why they
Right.
protect them. I mean, if you've flown a plane with a private plane or whatever, you every I don't know 5 minutes or whatever, you are in direct communication with the air traffic and say, your ID, like Jasper and 111, whatever, are you still there, and so on, and and you give your coordinates and all that.
Right.
For small planes, so they know exactly, and they direct you. I mean, so they know
Okay.
what you have. But now, if we are envisioning a future where this may be more loose, in other words, the airplanes are more autonomously directing themselves and so on and so forth, coordinating, then that's a different story where we may have that. I mean, this is so that would be something to think about. And
Right.
another thing that I just thought about from how is centralized this discussion of the centralized control and centralized collision avoidance is interesting. What you said about this, we call it partial centralization, in multi-agent systems, where you do have a leader or a controller for a small number, but the point is in the neighborhood, right? But
Right.
as they move, if you are thinking now of a swarm or multi-robot systems, as they move, their neighbors, of course, change.
Right. Right.
Now it would be interesting to say, okay, what would be now my overall coordination of actually changing, and and what would be the handoffs in terms of the mathematics, right?
Right.
Because now my my controller, if I am a robot, changes the leader, and how do the leaders, are they from the beginning, elected? Are they emerging? For example, the ones that may have the closest neighbors and so on. But as they move, how would that work? This partial centralization. I think that's a very interesting problem as well.
Right. I just like thought that off the top of my head. I'm pretty sure somebody must have done that before, or I'm not sure if there is prior work on that idea.
Well, there are for the changing, for example, so we've done we've done work with core set, for example. So now as you move, the core set of the swarm will change. So which are the members of the swarm that would be inside? So what's the core set? The core set is the one that characterizes the ellipsoid.
Right.
In volume. Okay, so now as you can imagine, as the swarm moves, members that were on the core set, parts of the core set, would fall off, would be internal members, and some other ones. And so this is sort of this idea of this
I
partial
see.
as a changing thing. This is the ellipsoid changes. So if you can imagine now a human operator that wants to control and know where now, do the system identification of where the swarm is, right? Then this ellipse will be changing.
Correct. Yeah.
So, and then there are some other schemes for partial centralization, but in different problems. So basically, if your bottleneck changes in your space, then your partial centralization would be, I want to have my bottleneck agent be the one that, for constraint satisfaction, for example, constraint optimization, be the one that would be controlling this constraint because it's the most constrained agent.
Correct.
And the most constrained agent can be changed. So if you have scheduling problems, for example, this shows up. It's the moving bottleneck kind of problem. So in any case, but they are in different domains even. But
Okay.
yeah, but that they could be ideas. I mean, if you want to attack that problem, there could be ideas from these other literatures, for example. But it is an interesting problem, because then you can really avoid partially, I mean, locally kind of avoid deadlocks, but then you need to do it for the whole system.
Okay. Got it.
So that's all I have.
Can I respond to one
Yeah.
Kadi's points?
Yes.
So one thing is Kadi made 2 points about the symmetry in 3 dimensions. About 3 dimensions, and the other one was about the confined spaces. So the symmetry in 3 dimensions, I think that would be a fun, interesting problem to worry about. But I think you'll end up worrying about all sorts of crazy types of crystalline symmetries that may never occur. So that's one concern. But you can do it. I mean, you have the ability to do it. I'm not suggesting what you do. And then in terms of the rareness of these kinds of collisions, maybe I was wondering how obstacles fit into your framework, or what would that be as an additional repulsive function on your controller? Because I think while collisions are rare events in 3 dimensions, but I would imagine they're less rare when you're in a confined space, flying through a building, let's say.
Right. So the way static obstacles are treated is you just say that they're non-cooperative. So they're not going to share the responsibility of avoiding collisions with me. And so as for the static obstacles there, I'll be fully responsible for avoiding collisions with the static obstacles. Whereas when they're moving robots, then I can distribute that cooperatively. And another thing, you mentioned the word crystalline. I did look at some chemistry things to look at configurations and how stable configurations are made in salts, to see if I could draw some parallels between the configurations that our systems converge to just see to see if there's some minima of some, like when I was saying, some energy function that corresponds to the asymptotic configuration of the robots when they will be in deadlock. But it was pretty dense, so I left that train of thought.
Yeah. I'll be quiet. Thank you.
Okay. Are there any other questions from the audience? Well, I hear none. So now, please, everybody leaves the room except for the everybody, including Jasper.
Cool. Interesting. So if I end the meeting, then
don't end the meeting.
Let us be the host, and then